There we go. All right, is everybody on board so far? This is all pretty easy, so I'm not too worried. Okay, so we have an idea of what temperature is. We know it gets exchanged between two systems. When it does, they exchange energy in the form of heat. Cool. Now, are there any other types of things that can get exchanged in a system? So actually, let's go back real quick. Let's make sure that we're clear here. So this is going to be called equilibrium. So the system has come to equilibrium when whatever quantities we're talking about have stopped changing. So are there any other types of equilibrium? Anybody? Well, okay, so we can come to thermal equilibrium, which is coming to the same temperature. We can come to what's called mechanical equilibrium. So an example of that is given in the book, and it is a balloon and air. So if you take the system that is a balloon and the air within the balloon expands as you put in air, and then at some point you put in as much air as you've got, and the volume of the balloon is just whatever it is. So in this case, well, I guess you could be changing the temperature of the balloon too, but let's just suppose that the air and the balloon are at the same temperature. But in this case, what we're going to call this type of equilibrium is going to be mechanical equilibrium. And the exchange quantity is going to be volume. So the air is taking up the volume that the balloon once occupied. And once that process comes to a halt, the type of equilibrium that we have is called mechanical equilibrium. Okay? There's one other type of equilibrium that we'll discuss here, and that is called diffusive equilibrium. And the classic example of that, does anybody know? Is there anything anybody drinks on a regular basis in the morning that's hot and black and is brewed with ground beans? Maybe you add cream to it, or I don't know. Oatmeal, yes. I hope your oatmeal is not black. Yes, coffee. What are you eating, Carter? You must have answered that question before I fully was done talking. So you do eat oatmeal in the morning. Oh, you're just being funny. Cool. You drink oatmeal. Yeah. I've never done that before, but maybe I'll give it a shot. So yeah, coffee. So the classic example is that if you take a system to be like coffee and cream, initially they're separated. And if you pour the cream into the coffee and you wait a long time, it comes to what we're going to call diffusive equilibrium. And what does that look like? Well, you know, it looks like the cream and the coffee have just combined into one thing. You could not possibly separate them ever again. And we're going to say that this thing exchanged here are the particles of each. So the particles of coffee and the particles of cream get all mixed up until they come to an equilibrium. Okay, so we've got mechanical, we've got diffusive, and then we've also got thermal, which we've already talked about. Okay, so at this point, I wanted to just have a quick aside and say that now that we've kind of discussed all the types of equilibrium, so all types of equilibrium, that the focus of this course, and yeah, I mean, the only thing that we're actually going to talk about in this course are different types of equilibrium. But you should really, really be cognizant of the fact that thermal and statistical physics, it doesn't just deal with equilibrium physics. There's an entire branch out there called non-equilibrium mechanics and non-equilibrium thermal and statistical physics. And that's like one of the most important things in the world. And obviously, like almost all systems are not actually in equilibrium. So this is a very, very large approximation that's only really suitable for idealized cases. But that's how you work in physics. You start with the simple stuff and then you work your way up. So just so you're aware. All right. What time is it? Oh, wow. Okay, so let's write down our definition of temperature now. So temperature. So we're going to say that temperature is a measure of the tendency of an object to spontaneously, and this is the reference to what we call heat. Yeah. Give up energy to its surroundings. All right. And if two objects are in contact, the one with the higher temperature is the one that loses the energy. So best way to write that is just with a picture. So if we've got T1 and we've got T2, and T1 is greater than T2, then we call T1 hotter than T2. And we think of the equilibrium process as being T1, call that 3. T1 is giving its energy to T2. So through this process right here, T1 loses heat. Okay, so this is just how we're going to think about energy and heat and transfer from this this position to equilibrium. So now, how would you build a thermometer to measure the temperature? Do you have any ideas? How do you actually measure this quantity called temperature? Feel free to unmute yourself at any point in time and just shout. Mm-hmm. Yeah, that's actually a good one. We didn't talk about heat making things expand yet, but it is true, actually, that that's a general thermodynamic rule that things typically expand when they get hotter. Keep in mind, this is not true for phase transitions necessarily. So it's a well-known fact that water, when it freezes, right, it gets colder, but as soon as it freezes, it's expanded, right? So its volume is actually bigger when it's colder. But in general, things get bigger when they heat up. So things bigger and hotter. Okay, so we could definitely use that to make a thermometer. Yep. Any specific ideas of how to do that? I mean, you're probably all familiar with some basic thermometers, right? So like mercury in a tube, what's happening there? Well, the liquid is expanding as it gets hotter. So that is thermal expansion of a liquid, more specifically. And liquid is just a specific state of matter. You could have a thermocouple, which is basically just something that has a temperature-dependent change in potential across 2 points, across 2 metals. We won't focus on that too much. You could also have thermal expansion of solids, so like a coil thermometer. Basically, you have, in that at least, it's going to be actually on the homework, but you have like one metal and then you have another metal, and think of them as being fused to each other. If they expand at different rates, then there's going to be stress that makes one of them expand faster than the other, and so they'll kind of like curl, right? Because there will be stress, like this one will expand faster, and so it'll kind of turn the other one around. So that's how kind of dial thermometers work. So this is a dimetal. Solids. And all right, another one that we could have that should have gone in there should have been gas. And that's actually the interesting one that's going to take us to our next topic, because of particular interest for expansion of gases, if you take the temperature and you send it to 0, then you find that the volume occupied by the gas goes to 0. Not equals 0, goes to 0 for fixed P. And P here is just pressure. And that's neglecting phase changes. And also vice versa, you find that as T goes to 0 for the case of fixed volume, that the pressure goes to 0. So these are things that you could figure out empirically if you were to test them on a bench of some type. So this is going to be very manifest when we talk about the ideal gas law in just a few minutes, potentially. So let's see. So what are, so what are the units of temperature, basically? And before we talk about that, we want to say that basically what we had said here before, that when T goes to 0, V goes to 0, that this temperature, T equals 0, has a special name that we just call absolute zero. And we build a lot of different unit systems around that temperature. So let's just go to the next page. So T equals 0, in that case, is called absolute zero. And that temperature defines what we call the Kelvin scale. So it's actually 0 Kelvin. And it's not degrees Kelvin. So on your homework, do not ever write like T equals like 30 degrees Kelvin, just because nobody in the world does that. I mean, you might write like degrees Celsius or degrees Fahrenheit, but don't do that. Okay. So unfortunately, this temperature, it's not accessible to us. So it's not really a very useful scale to work on for the most part. So in real life, we generally define a different scale, which has the exact same increment. And what I mean by that is that like going from T equals like 20 Kelvin to T equals 50 Kelvin is actually like the same change in energy. So a different scale that we define that has the same increment in energy of going from one temperature to the other is just Celsius. So the Celsius, whoop. So it has the same increment. But T equals 0. Hold up. Well, yeah, so T equals 0 degrees Celsius corresponds to water freezing. So T equals 0 Kelvin is absolute zero. The Celsius scale just moves everything up. It's just an offset to the Kelvin scale. And so most things in thermodynamics are going to be defined in terms of the Kelvin scale, so just be very careful of that. So I'll write that. So be careful to pay attention to units. Because, for example, when we get to the ideal gas law in a few minutes, if we even do that right now, if you put in T in terms of Celsius, you'll get nonsense results. You won't get the previous result that T goes to 0 implies that V goes to 0. You get something totally different. So be very, very careful about this. I'll even star it. All right, so before we adjourn, I'd like to do just a quick problem which kind of starts the homework for you guys. And that is basically problem 1.1 from Schroeder. So I guess this will be technically like a bit of a tutorial. And if you need to leave, you can feel free to. But that's totally up to you. So what we want to do is we want to figure out how to convert between Celsius and something that we'll call Fahrenheit. Okay, just two different units of temperature. So what we'll know empirically is that water freezing corresponds to 0 degrees Celsius, which is how we define Celsius. And on the Fahrenheit scale, it corresponds to 32 degrees Fahrenheit. Okay, you all know that, hopefully. And we'll also say that we have empirically figured out that water boils at 100 degrees Celsius. And in Fahrenheit, that corresponds to 212 degrees Fahrenheit. So we want to figure out how to go from T in Celsius to T in Fahrenheit, just put an F, and vice versa. Any ideas? Oh. Yes, yeah, we're going to assume that they're both linear scales. It wouldn't be very useful to have a temperature scale that wasn't linear. It'd be kind of weird, but that's a good question. So yeah, I mean, if we know that it's linear, what could we write? We know that, like, how can we write lines in general? Everybody knows this, right? Equation of a line. Yeah, the slope and intercept will tell us everything we need to know. So for example, if we want to write T Fahrenheit in terms of T Celsius, we could probably assume, if we know that it's linear, that it's going to be something like this, where m is the slope plus some intercept b, right? So now we just got to figure out what this slope is and what this intercept is. So how might we do that? It should be, yeah. Yeah. So, yeah, I mean, we see that what we call 0 here has to correspond to 32 here, right? So you can just see if you were to plug in, let's just do it. Let's plug in 0 degrees Celsius. So TF equal, so yeah, we know that this should be 32 degrees Fahrenheit equals TC, which is 0 degrees Celsius. So it doesn't matter what M is, that whole thing is just 0 plus B. So it's obvious that B is equal to 32 degrees Fahrenheit, right? That's good. So we'll box that. Now, how might we figure out the intercept? Is there any way we could use something called dimensional analysis? Is anybody familiar with that? It's basically just analyzing units and making sure the units work out. So what I'm going to use to denote dimensions in this class is going to be just square brackets. So for example, me putting square brackets around TF is just saying, just select out what those units are. Well, the units here are degrees Fahrenheit, right? The units of TC in Celsius is degrees Celsius. Okay, well, we know that this entire equation here, each side has to have the same units for it to be a consistent equation. So if we take the units of it, TF equals TCM plus B, we know overall that it has to have units of degrees Fahrenheit equals degrees Fahrenheit, right? So if we know that TC has units of degrees Celsius, what units must M have? Anybody? Just 1 over degrees Celsius? So if we took M times TC, which is degrees Celsius, then this right here would be unitless, right? Because you'd have degrees Celsius over degrees Celsius. Yeah. So degrees Fahrenheit, oh, why did that get so dim? Degrees Fahrenheit over degrees Celsius. So if we multiply that, M by TC, then the degrees Celsius cancels out and you're just left with Fahrenheit. Okay, so we know what units it must have. Now, how might we find the actual value? So wait, say that again. Take T Boyle T212 and do what? Why the y-intercept though? Well, I mean, I get in this case, it actually will be the correct answer. But in general, what we want to do really is we want to compare the scalings between these two units. So basically, 32 degrees Fahrenheit here corresponds to 0, which is the y-intercept. But in general, the way you'd want to think about this is m is going to be equal to 212 degrees Fahrenheit minus 32 degrees Fahrenheit. So you're taking the difference between those two temperatures, because you know that they correspond to the same temperature. You know that 212 and 100 are the same. So if we divide by what the scaling is for Celsius, be 100 Celsius minus 0 Celsius. Yeah, that'll be what our slope is for this line. Okay, so what does that come out to be? Anybody? 18, is that right? All right, so we've got M, we've got B, so we know what TF is in terms of TC. Now to get TC, you would just invert this whole thing, right? So TC is going to be equal to TF minus B times what? M? 1 over M? 1 over M, right? So we're just taking this formula right here, which we know relates Fahrenheit to Celsius. And we're going to solve it for T Celsius. So all we got to do is move the B over to that side, so subtract it over, TF minus TB, and we got to divide by M, so 1 over M. So now we've got, this is our conversion, and this is our conversion, and we have all of the other pieces we need. We've got the slope, we've got the y-intercept. So now in practice, we could do the whole problem. So this is where I'll leave you with this problem. It is the first problem in the homework set. With what we've started right here, I think you should be able to finish the rest of it, no problem. But if you do have any questions, just let me know. All right. So I think that will end where I wanted to get with this lecture, which is good. We only went 10 minutes over, so great. So yeah, next lecture we'll cover the ideal gas law and get as far as we possibly can with that, and then we'll finish the chapter on Friday. So if you want to stick around for office hours, feel free to. If you want to come to office hours on Tuesday, again, feel free to, but otherwise we'll see each other all again on Monday. Does that sound good? Anybody have any questions in general? I know this is pretty basic material, so you might not really have a lot to say, but trust me, it'll get worse real fast. Don't take that to be like a bad thing. It'll get more fun really fast. All right. Okay, well, I will end this meeting and I'll open up my Zoom office hours, and if you want to join, you're more than welcome to. The link is on the syllabus. Okay, so it was great meeting you all, and I hope that the rest of your day goes well. So I'll see you later.